So here is another static equilibrium problem involving torque. There's a beam. It is held in place by a cable. And the question part A asks you to find the tension or the magnitude of the tension. And then part B asks you to find the force by the hinge on the beam. And in the diagram, the hinge is against the wall here. While there is a force exerted on the hinge, the force by the hinge contribute no torque because the hinge itself is the pivot in this particular diagram. So while there is a force, there is no level arm. So F times 0 will just give you 0, which generates no torque. Okay, so the first thing I suggest you do is draw all your forces. This way it helps you with setting up the torque function. So the first thing I have drawn here is the weight of the sign in green. So F of G, comma S, S for sign. The next vector here I have is the weight of the beam, which is placed at the center of mass of the beam. It's important that you place that vector at the center of mass. Sometimes kids have a misconception and they place at the end of the beam. And then the next vector that's obvious is the tension in the cable, and that vector is pointing in the upper left corner because it is directed towards the ceiling, which is what's holding the beam up. And then from there, you can go ahead and break T up into its vertical and horizontal component. So in this case, there's T, and the dashed line represents the vertical component of the tension, and then the horizontal component is drawn there in the yellow dash pointing to the left. Because the force vector T is in the second quadrant, you have to have a horizontal component negative, and the vertical component must be positive. Okay. The next thing you should do is find your level arm for F of G due to the weight of the beam in purple there from the pivot measured to the center of mass, and that'll be a distance of half of 1.3, which would be 0.65 meters. And then in green, towards the bottom of the diagram there, that level arm is measured from the pivot to where the force is, and that in this case will be a distance of 1.1 because the whole entire beam is 1.3 and it's zero point 0.2 from the right, so the difference there is 1.1. Okay. And then the next thing is that you notice Ty is placed at the very end of the beam, so the level arm for that particular component of the force vector will be just the entire length, which is 1.3. So everything is already perpendicular because we need torque. So if you set up net torque function, which is equal to 0, again, because the system is being held in place, aka static equilibrium. So you can just set up your torque in the counterclockwise direction equals torque in the clockwise direction. So if we look at this particular schematic, we notice here F of G naturally, if you release it, the beam will rotate clockwise, and the weight of the sign will also cause the beam to rotate clockwise. So we have two vectors here that will contribute to the clockwise rotation, while tension, the vertical component of the tension, will cause the system to rotate counterclockwise. So we have a balance here, a clockwise and a counterclockwise. So the work I have set up here is counterclockwise, which is Ty times L. Again, Ty is going to pull the system counterclockwise, if you can kind of visualize that. And the weight of the sign times its moment of arm plus the weight of the beam times the moment of arm will cause the system to rotate clockwise. So you wanted to set those two functions equal to each other because the net torque must equal to 0. And then you can just expand from here, which is some detail or tedious math here. The vertical component of T, which is Ty, based on the angle given, which is 62 here, would be the opposite. So we want to do T sine of theta times L, and then replacing F of G, which is mass times gravity. Also, we're doing the same here for the weight of the beam or the force of gravity due to the beam in this statement. And then we substitute in everything that we know. The problem gives us an angle of 62 degrees, and the length of the beam is 1.3 meters as drawn here in the diagram. The mass of the sign is 16 kilogram down here, G 9.8, and then the moment of arm for the sign is 1.1 again, because if you watch my cursor, this whole entire beam is 1.3, and then the distance from here to here is 0.2. So we want to take the difference. So 1.3 minus zero point 0.2 gives us this level arm, which is 1.1 in green. And we do the same with the weight of the beam. And again, for RB here, you don't want to plug in 1.3. You actually want to just plug in half because the force of gravity on the beam is at the center of mass, which is half the length. And as you can see in the statement, the only thing left unknown is t. So some basic calculator work, which I've done for you here. I simplify everything on the right side, and you should get 197.96. And then sine of 62 times 1.3 on the left side gives us, in the parentheses, 1.15. To solve for t, divide both sides by 1.15, and you should get a magnitude of 1.7214. And that's it for part A. It's pretty straightforward. Okay. So here comes part B. So for part B, you do need these forces that just came up on the screen in blue towards the left here. Again, there is a force on the hinge, but there is a force pushing to the right because you do need a force canceling out this TX component because nothing's moving. And then there is also a vertical force on the hinge. And as a result, the net force exerted by the hinge will be this diagonal because it does have a y and a horizontal component. And I'll show you how to do part B in the next slide. So I highly suggest that you set up this little chart just to help you organize your information. I have here x and y. So now we just want to set up Newton's second equation where a is equal to 0 because nothing is moving. So therefore, if you look at this particular diagram, I have everything set up for you. Horizontally, you have the force H in the horizontal direction here, which is H for hinge. And then you have a TX component pointing left. Because the system is not moving, this component rightward and this horizontal component leftward must equal. So therefore, we make the statement in the work next. The horizontal component on the hinge must equal to the tension in the x direction. And then from there, you can just do basic math. We already found T in the previous part A, and then Tx in this case, Tx runs along the adjacent of the angle 62. So we want to use cosine of 62. And then solving for F, the force due to the hinge in the horizontal direction, which is BT cosine of 62. And then that will give us this particular value of 80.8. And then moving on to the y direction, same format, except the y direction, you have a little more going on. So if you watch my cursor, there's the weight of the beam directed downward. There's the weight of the sign directed downward. And then the vertical component of the tension, which is Ty, pointing upward. And I went ahead and calculated that for you. That value is 152 newtons. And then if you look at the left side of the cursor here, we do have another vertical component due to the force of the hinge in the y direction. So you have two vectors pointing down, you have two vectors pointing up. So I color coded for you here. I added everything that's pointing up, I subtract everything that's pointing down, and I set that statement equal to 0. And then from here, we just do calculator work. Okay. So if you plug in everything you know, again, Ty I solved for you already in this diagram. If you do T sine of 62, using the T values, going to part A, you get a 152. And then the weight of the beam and the weight of the sign is pretty straightforward. It's just mass times acceleration due to gravity. And then from here, the only thing unknown is the FH in the vertical direction. So we solve for FHY, you'll get 44. But that, we can't stop there because the question is not asking for the vertical horizontal component, it's actually asking for the vector itself. So to find FH in this diagram, this diagonal, you would just have to do Pythagorean theorem. So I'll fly through this. Write out Pythagorean theorem, plug in your FHX square, FHY square root it, and you should get a net force of 92. But because force is a vector, you do need to incorporate the direction. And to find the direction, it's pretty straightforward. All you have to do is do inverse tan of the y over the x component. Again, so this is the y component, and that's the x component. You can find this angle above the beam. So if you plug in everything you know from the previous work, up here we just found FHY is equal to 44, FHX is equal to 80.8, and we plug that in, and you should get about 28.6 degrees, and that is where that angle is. And that's it. Thank you.